Hello, Jake. How are you?
Good. How about you?
Good. It's stretch time. I've got
Yeah.
you and I got one more tomorrow morning, and then I'm got a nice little vacation coming up.
We got one tomorrow morning.
I do. I got somebody that's taking a calculus test on Thursday.
Oh, jeez.
Uh, but yeah, no, it's been busier than heck for me for like 3 weeks, which is great. I love it. I love being busy like that.
hmm
So when is your test?
My finals aren't until next year.
Oh, okay. So what are we working on tonight?
We're working on trig here.
Okay, is it stuff you can verbalize, or do you need to send me a picture of something?
I'm not very sure. Here, let me find the problems real quick.
Okay. Trig can be, you can have a lot of trig problems that you could verbalize, but there's a lot of trig problems that you wouldn't be able to verbalize also. You know, if they're asking you to give the sinusoid function of a sinusoid graph, then that's something that can't really be verbalized.
Okay, so we're going over like graphs of trig functions.
Okay, that we can do without, you can verbalize that. So all you have to do is give me the function.
I was wondering if we could go over the base graphs for all of them.
Yeah, okay. Talk about the two most important, sine and cosine. This is sine. Now, I've only drawn one period of it. It obviously goes
Right.
on forever. In other words, it goes like that in that direction, and it goes like this in that direction. But the key points is it never gets above 1 or below -1. And it starts at 0, so that the sine of 0 is 0. Starts at 0, goes up to its maximum, turns around, comes down all the way to its minimum, turns around, goes back to 0. There's the starting and ending points circled. And let's label them, because these labels are key. That's 2 pi. That's pi. The peak is at pi over 2, and the bottom is at 3 pi over 2. Now, I'm assuming that you're dealing mainly with radians now when you look at graphs as opposed to degrees. Am I correct?
Mm-hmm.
All right. In other words, 2 pi is the same as 360 degrees, so I could label that. And I could label that 270 and that 180 and that 90. But by the time you get to this part of trig, they're usually using radians only. And one of the reasons for that is that when you get to calculus, it has to be in radians. Calculus does not work if you use degrees. When I'm in calculus and I say the first derivative of sine is cosine, that's only true if it's in radians. It has to be in radians. So when you get to calculus, they pretty much have converted you over to radians 100%. And so
Okay.
the x-axis that you see here is usually in radians, not degrees. Okay? Now, let's talk about cosine, next most important function. This starts at 1, not at 0. And that's huge, because most people that have trouble with trig have trouble with knowing what the cosine of 0 is. Again, the period is 2 pi. The period of both sine and cosine is 2 pi. And the part of the trick with trig is to divide up your curve into its quarter points. Notice that I've got 4 quarter points. Actually 5. The first one is its starting value. So the cosine of 0 is 1. You see why? Cosine of pi over 2 is 0. Cosine of pi is minus 1. Cosine of 3 pi over 2 is 0. And the cosine of 2 pi is 1. So your quarter points all produce these either 1, 0, or minus 1. And of course, this also goes in both directions. But the key thing to memorize about the graphs are one period of it. In other words, it doesn't do a whole lot of good to look at a non-ending cycle, but if I look at precisely one period of it, then I understand the function a lot better. And the third most important one is tangent. A tangent's different than sine and cosine. Tangent has some vertical asymptotes. Remember what that is from precalculus?
Mm-hmm.
Those vertical asymptotes occur at minus pi over 2, at plus pi over 2, and at every multiple of pi after that. In other words, 3 pi over 2, and so forth. And what does the curve look like? It's always increasing, goes through 0 at 0, and goes up to positive infinity. And we know one point on the curve, which is 1, is the tangent of 45 degrees is 1. 45 degrees is pi over 4. So this tangent curve repeats every pi, making its period pi, not 2 pi. The natural period of sine and cosine is 2 pi. The natural period of tangent is pi. In other words, the natural period being the distance from there to there, the red line. In tangent, that's pi. If I were to go back to my sine and cosine curve, then the period from beginning to end would be 2 pi, not pi. Okay? Now,
Okay.
have they talked to you about secant, cosecant, and cotangent?
No.
So you don't need to know the graphs of those?
I do, actually.
Okay. Let's talk about tangent, or cotangent, the reciprocal of tangent, since I have the tangent curve up here. I'm going to draw the cotangent curve. Well, the cotangent curve also has vertical asymptotes, which occur every pi, but the first two occur at 0 and pi, as opposed to tangent, which goes from minus pi over 2 to pi over 2. And the cotangent curve is always decreasing, going through 0 at, notice, pi over 2. But its range is negative infinity to positive infinity. The range of both tangent and cotangent are all real numbers. Notice what the range of sine and cosine are. Minus 1 to 1. That's it. Minus 1 to 1. There's no way the sine of any angle or number can be 1.2. Impossible. So the one thing about tangent and cotangent is if I said, let's graph y equals minus tan of x in green, I would take my black line, I would reflect it over the x-axis, and I would get this, right? With me? Notice how similar that looks to the red graph. So if I just arbitrarily gave you a curve and said that it's that, you would not know, if I didn't put any dimensions on there, you would not know if that was the minus tangent curve or is that the cotangent curve. Because remember, the red graph is y equal cotangent x. So the only difference between the cotangent curve and the minus tangent curve is where it's at on the x-axis. In other words, if my curve, the green curve, comes between minus pi over 2 and plus pi over 2, that means it's not a cotangent curve, it's a negative tangent curve. The red curve goes from 0, the origin, to pi. So if I saw a curve like this, and it's labeled pi there and 2 pi there, I know that's a cotangent curve. Do you see why? Because the cotangent asymptotes are 0, pi, 2 pi, 3 pi, 4 pi, and so forth. Whereas the asymptotes for the tangent curve are minus pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, and so forth. So their asymptotes are 90 degrees shifted from one another. So that's how you tell the difference between a minus tangent curve and a cotangent curve, is the x-axis. Now, let's talk about secant and cosecant. First of all, what is the reciprocal of secant?
Cosine.
So what that means is if I start with the cosine curve, and I'll even draw at least one more cycle of it to the left. Well, when the cosine of x equals 1, what does the secant equal? In other words, when I let x equal 0, cosine of 0 is 1, what's secant of 0 equal to?
-1.
No, positive 1. In other words, if I replace cosine of x with 1, I still have 1 over 1. So secant of x is still 1. 1 is the only number whose reciprocal is the same as it. There's no other number that's like that. 0 is not like that. 2 is not like that. 1,000,000 is not like that. 1 is the only number. So what that means is that when the cosine is equal to 1, the secant must also equal to 1. And the secant curve sits on the peaks and the valleys of the cosine curve. In other words, whenever cosine is equal to 1, secant has to be equal to 1. Whenever cosine is equal to -1, secant has to be -1. So the only way this thing can look is like this. Now, notice that when cosine is equal to 0, let's make that 1. make that minus 1. But notice when cosine is equal to 0, right there. What's the secant going to be?
Would it be not a real answer?
It's infinity, right? In other words, the secant also has vertical asymptotes wherever the cosine is equal to 0. So it's got a vertical asymptote there. It's got a vertical asymptote there. And these green parabola-shaped things you're seeing are not parabolas. They're secant. And one cycle of the secant is one of those plus one of those.
Mm-hmm.
And that goes from minus pi over 2, that asymptote. Well, that's pi over 2 right there. That's 3 pi over 2. So the period of the secant, and the period goes from this point to this point. In other words, when you're talking period of trig functions, you're talking to where it recycles again. Well, there's one point, there's the next point where it starts from positive infinity and heads down. So the distance between those red circles is the period of this function.
Self-infinity.
What's that?
Wait, what?
No, the period is always measured on the x-axis. So the period between those red circles is this distance here. From minus pi over 2 to 3 pi over 2. That's a period of 2 pi. Same as cosine, as it should be. And cosecant is very similar. It's the reciprocal of sine. So if I want to, let me go down a page. And I'm going to draw the sine again. And if there was ever any two curves you want to memorize, it's sine and cosine. And by memorizing it, I mean memorize these, every point that I'm putting on here.
All right.
And you only have to memorize one period of it. Okay, that's y equals sine x. Now, since sine x, let me write it this way. Since cosecant is equal to 1 over sine x, then whenever sine x is equal to 1 or minus 1, cosecant has to be the same thing. So in this case, the cosecant sits on the tops and the bottoms of the sine curve. And there's a vertical asymptote wherever sine is equal to 0. Because obviously if sine is equal to 0, then we got 1 divided by 0, which is either positive or negative infinity. And that's what my curve is showing. Okay? So your vertical asymptotes are going to come whenever its reciprocal function is equal to 0. And of course there's one right there. And again, the period of cosine or cosecant of x is 2 pi. And in fact, in this example that I've drawn, it goes from 0 to 2 pi, whereas secant went from minus pi over 2 to 3 pi over 2. So horizontally shifted a little bit. But the thing to really, really remember is that when the sine is equal to 1, the cosecant has to be equal to 1. When the sine is equal to -1, the cosecant has to be equal to -1. Remember the reciprocal, the only reciprocal that's equal to itself is 1 and -1. Sorry, not just 1, but 1 and -1. That's all 6 trig functions. Okay?
Okay.
So now here's a test. I'm going to draw them. You tell me what it is.
Okay. Cosine.
Good. That's meant to go through the origin.
Tangent.
Good.
Secant.
Sine. Sine starts at 0 and goes up. The only reason that this was confusing was because I drew an unusual period. I went from minus pi over 2 to 3 pi over 2. Instead of the normal way you draw the sine, the normal way you draw the sine is like this. But it doesn't matter where the period is on the x-axis. When I drew the black line, I drew one period of the sine function. That's one period of the sine function. And the only way to really recognize that that's the sine function is to look at what it does at the origin. It starts at 0 and it goes up to 1. Then it goes completely down to its minimum of -1. When I say it starts at 0, I meant that when x is equal to 0, y is equal to 0. Obviously, when x is equal to minus pi over 2, y is equal to -1. Hold on one second. Close my office door. Am I confusing you or not? I don't think so. You seem to be getting most of this.
Yeah, I get it.
Okay, let me keep going. The key is if you can recognize what the curve is. There's
Secant.
one. Good.
Cotangent. Would that just be the inverse of tan, or?
That is the negative tan, not the inverse. It's not the inverse, because inverse means something totally different.
That's what I meant. Sorry.
But that's a negative tan. No, remember when you're doing transformations what the negative sign means. The negative sign in front of the function means you reflect it over the x-axis. Well, the tan function looks like this. So that original black line that I drew is merely a reflection of the tan function. That makes it negative tan. As opposed to if I would have drawn it like this, you correctly identified that as cotangent. So the red line is y equal cotangent x, but the black line, this one here, is y equal minus tan x. Okay, so that's the way it works. Let me keep giving you some because this is huge. If you can understand this, and it seems like you are,
What's this one?
well, yeah, what is it?
Negative sign.
Very good. In other words, we're looking at the sine curve that's been reflected over the x-axis. The unreflected curve would have been looked like that, which we should have recognized immediately as sine x, and you recognized negative sine x. Okay? Oops, hold on.
This would be negative secants.
Very good. That's exactly what that is. Now, looking at this curve, tell me what the domain is.
Would it be
Remember, we have vertical asymptotes. Everything has vertical asymptotes except sine and cosine. All the other 6 trig functions have vertical asymptotes. So how would you describe this domain? First of all, that's pi over 2. That's minus pi over 2. That's 3 pi.
so it would be all real numbers except for minus pi over 2, 3 pi over 2.
You got it.
2.
You got it. And the way you would write that is all reals except x cannot be equal to any multiple of pi over 2, where n equals 1, 2, 3, and so forth. Sorry, that's not right. Here's the way you describe the domain. You got it wrong. It's all reals except x cannot be equal to pi over 2 plus multiples of pi, where n is all integers, not starting just at 1, 2, 3, but n can be negative. In other words, n is integers only. And notice how that works. X cannot be equal to pi over 2. It cannot be equal to 3 pi over 2. It cannot be equal to 5 pi over 2. And that's what that says right there.
Mm-hmm.
More importantly, what's the range?
The range?
The y-axis, the range is always the allowable y values.
Would it just be infinity?
Negative infinity, always start from the bottom.
Negative infinity to negative 1.
Bracket or parentheses.
Bracket.
Good.
And then 1 to negative infinity, bracket 2.
1 to positive infinity.
Yeah, it's not that infinity.
Infinities always get parentheses. You never see a bracket next to an infinity.
Yeah.
Because it's not a number, it's a concept.
Mm-hmm.
So something can't be infinity. Okay?
Yeah.
You can approach infinity. But it is allowed to be 1. In other words, I can be 1 and I can be negative 1. And that's what those values are there, is 1 and negative 1. So knowing the domain and range of all your trig functions is fairly key. Let's look at the tangent function again. What's the range of the tangent function?
The range would be negative infinity to positive infinity.
Correct. Describe the domain.
The domain...
Here, I'll help. In other words, the domain is very dependent on where these vertical asymptotes are.
Yeah.
How would you describe that domain?
All real numbers except for negative pi over 2, pi over 2, 3 pi over 2, and then pi.
And the way you describe that is you give the first one plus multiples of pi. Notice that n can be any integer number. It can be minus 100, minus 99. It can be 0. It can be 1. When it's 1, I'm right there. When it's 2, I'm right there. When it's 0, I'm right there. So this answer, kind of get used to it because you're going to see that. It's an unusual way to describe domain when you have repeating vertical asymptotes. In other words, you don't really get repeating vertical asymptotes when you're talking about polynomials or rational quotients. You never do. It's only when you get to trig that you have repeating vertical asymptotes, and they require this kind of new notation where we use this letter n. They may use k, they may use something, but that means all integers, or any integers is what that means.
Mm-hmm.
All right. Well, that's a pretty good 101 of trig graphs. Do you have
thank you.
Do you have some specific problems that we can do? In other words, I'm not quite sure how far they've gotten. What have I said?
I didn't have any homework for tonight.
What have I? Okay, well, I can keep going. Have you gotten sinusoid?
I was wondering if you go over like periods and amplitudes and stuff like that.
Okay, that's the sinusoid function. Let's talk about that. The general format of the sinusoid function is there's actually multiples. This is the one I like the most. But you might also find this one. It just all depends on your school system, where the b is inside the parentheses, like this. Okay? So you most likely have one of these two. And it doesn't really matter what they teach you. What matters is what function they give you. If it's in the second format, then you have to know what this means. If it's in the first format, B is actually defined a little differently, and so is C. Let's talk about what each letter means. A is amplitude. So let's look at a simple situation. Y equals 2 sine of x, which would mean B is 1, C is 0, D is 0. With me?
Yeah.
If I were to graph y equal 2 sine of x, that's a what? That's a vertical stretch by a factor of 2, correct?
Yeah.
So the regular sine curve may look like that, but this curve is going to look like this. It's going to be a vertical stretch by a factor of 2.
Except the x-axis at the same points.
Right. It has the same zeros, but notice the range all of a sudden now goes from -2 to 2. So it's perfectly possible for that number to be 2. But what can never be more than 1 or less than -1 is the sine of x. If you add a vertical stretch factor in front, well then, of course, it can be anything. If that's 100, it would go up to 100 and down to -100. So that's what amplitude does. Amplitude is a vertical stretch factor. That's all it is, a vertical stretch factor. And it looks like it. It's in front. And in fact, all of the transformations you learned for polynomials apply to trig functions. I've never understood why our education system treats it like it's a completely different beast, because it isn't. These are all exactly the same. That's vertical stretch factor. That's horizontal stretch factor. That's horizontal shift. That's vertical shift. If I put a negative sign in front of that, that's a vertical reflection. If I put a negative sign in front of the x, that's a horizontal reflection. So it's exactly the same as polynomials. For some reason, when they teach you trig, they don't tell you that. I'm not sure why. I really do not know why. It would be a lot easier for trig students if they knew that this A, B, C, and D were vertical, horizontal stretches, horizontal, and vertical shifts. Now, let's talk about the letter B. Maybe this is why they don't teach it this way. B is related to the period by 2 pi over the period. That's what you have to memorize, which means the period is equal to 2 pi over b. So let's say I said to you y is equal to the sine of 2x. Different than what we just looked at. The previous one was 2 times the sine of x. Okay? What's the period of this function? The period being the distance between there and when it ends. In other words, what is it?
Pi.
Correct. So that's pi for this function, which means when I quarter it up, which you always have to do, that's pi over 2, halfway between 0 and pi. That's pi over 4. What's that point? What's halfway between pi over 2 and pi?
3 pi or 4.
Pi over 4, exactly. So this function is exactly the same as the sine curve, only the sine curve would have done this. The sine curve would have gone up there, down through pi, and back up to 2 pi. So the black curve relative to the red curve is a horizontal crunch, right? Or shrink, whatever you want to call it.
So it just increases the frequency.
It affects the frequency. The frequency is the reciprocal of the period. So I know that some classes focus on frequency. Most trig classes do not. In fact, out of every 10 trig students I have, only one of them will even mention the word frequency. It's real easy. Frequency is merely the reciprocal of period. But that doesn't really affect too many things until you start getting into word problems that give you things in frequency. The key is to understand the relationship between B and period. When B is a number greater than 1, it horizontally shrinks the function. When B is a number between 0 and 1, it horizontally stretches the function. In other words, I would have given you sine equals x over, sine of x over 2. Now what's B? What's B for that right there?
2.
1/2. Can't be 2. It was 2 in this situation, and these clearly are different. It's 1/2. This is the same as if I wrote y equals sine of 1/2 x. Don't be fooled by the fact that I put the fraction bar and didn't write the 1. Those two things are the same. And plug in that, so b is 1/2. Plug in b there. What's the period of this function?
Pi.
What's 2 pi divided by 1/2?
It's 4.
4 pi. Okay? So the effect is that I stretch out my function. The red goes from 0 to 2 pi, right? The black went from 0 to pi. Well, if my period is 4 pi, I got to go off the page. I got to even redraw it here. In other words, 4 pi means this point right here is 4 pi. And then if I quarter it up, that's 2 pi there, that's pi, that's pi, 3 pi. Notice that the quarter points are always the key points of the function. That's where the function is at its maximum, or 0, or its minimum, or back to 0. So those are really important points to understand. That's why no matter what the period is, you end up quartering it up. You with me?
Mm-hmm.
All right. Let's talk about C. First of all, I don't want to erase any of this. I'm going to get rid of frequency because that just adds to the confusion at this point and does not really enlighten us, as long as you always remember that frequency is 1 over period. C is a horizontal shift. So C, they don't like to call it a horizontal shift. They call it a phase shift. It's the same curve shifted left or right. The problem is that each format is different. In the top row, C is the phase shift. In the bottom, the second row, C is not the phase shift. I've got to factor that B out, and when I do so, I end up with C over B. So if I rewrite the second equation, factoring the B out, I get B times X minus C over B. Notice that equation 1 and equation 3 are the same. Equation 2 is different. So when I'm talking about the phase shift, it's very, very important what form they give it to you in. And as an example, let me give you a certain form. Which equation does this look like? 1, 2, or 3?
On 1.
1, right. The B is outside the parentheses. How about this one? You see the difference? Does not change the period. B is equal to 3 in either case, and the period is equal to 2 pi over B. So it does not affect the period. What it does affect is the phase shift. We're going to talk about the phase shift in a minute, but you can think of a phase shift exactly as you think of a horizontal shift. It does not change the shape of the curve, it merely moves it left and right. The difference is in this equation, 1, the phase shift is pi over 2. In this equation, 5, that's not the phase shift because I got to factor out a 3, so I got to rewrite it or else know that the phase shift is C over B. Let's just use that formula instead of rewriting it. So the phase shift for this one is pi over 2 divided by 3, which is pi over 6. The phase shift for equation number 1 is pi over 2. So depending on whether that B is inside or outside the parentheses makes quite a bit of difference. as to what the phase shift is. Now let's just talk about phase shift for a second. If I give you a function and I say y equals sine of x minus pi over 4. B is 1, so it doesn't matter if it's inside or outside. The phase shift is what?
Pi over 4.
To the right, correct?
Yeah.
So I would take my sine curve, which goes from 0 to 2 pi, and I would shift it pi over 4 to the right. So the very first point comes at pi over 4, not 0. And now if I quarter that up, the red curve, this is 9 pi over 4. The beginning is pi over 4. The middle point must be 5 pi over 4. This point here, where it reaches its maximum, must be 3 pi over 4. And this point has to be 7 pi over 4. In other words, sometimes when you quarter it up, it's not so easy to come up with the quarters. You know, it's not that easy to come up. But if you notice, the difference between pi over 4 and 9 pi over 4 is 2 pi. So the period of my red curve is still 2 pi. But it's been phase shifted from the black curve. It's exactly the same shape. It does not change the range, domain, or anything like that. Doesn't change the period. It just starts it in a different place on the x-axis. And that's what phase shift does. That's what horizontal shift does, right? In other words, if I graph y equal x squared, it looks like this. But I put a horizontal shift in there, y equal x minus 2 quantity squared. And it takes that red curve and moves it to the right by 2 units, exactly the same shape curve, like that. Well, that, what we call a horizontal shift with a polynomial, is called a phase shift with a sinusoid function. And incidentally, one other thing about sinusoid functions, they don't have to be sine. They can be cosine or sine.
Okay.
And the general rule is that you choose the one that has the least phase shift. For example, in other words, you've got to be able to go both ways on these things. If I give you a sinusoid function, you need to be able to graph it. But if I give you a graph, you need to be able to know what it is. It's the period of this function. Difference between the first starting spot and the next starting spot.
4 pi over 2.
Which is 2 pi. So what's B? If the period is 2 pi, B is 1. Because remember, B is 2 pi over the period. So if the period, we just looking at the graph, we can tell the period is 2 pi, therefore B is 1.
Okay.
So I know B is 1. Let's say this function goes from 1 to minus 1. What's A?
A, 1.
Good. So I know A, I know B. What's C?
Let's see.
C is the phase shift.
That would be plus pi over 2.
Okay. So C is pi over 2. And in this example, d is 0. D, incidentally, is the vertical shift. It's the easiest thing of all.
Yeah.
It's just like a vertical shift with polynomial. Does not change the shape, merely moves it up or down. Okay? So I could write this as y equals, a is 1. I'm going to use the sine function. B is 1. It does have a phase shift of pi over 2, so I'm going to write it like that, plus 0, because d is 0. But notice that there's another way I could write this. That point right there is pi. So I could write it as a cosine curve. Exactly the same, only the cosine curve has been shifted by pi, right? From a normal cosine curve. In other words, a normal cosine curve starts there and goes like this. Well, if this is the start of my cosine curve, it's exactly pi to the right of a normal cosine curve. So I could also call this black curve a cosine curve that had been phase shifted by pi instead of pi over 2. So any curve that you can call sine, well, you can also call cosine with just a different phase shift. The only difference between sine and cosine, if you'll notice the two curves, I'll draw them on top of one another. I'm going to draw a sine curve, and then I'm going to draw a cosine curve. The only difference between them is if I took my red line and shifted it to the right by pi over 2, because that's what this mark is pi over 2, it would look exactly like the cosine or the sine curve, right? So I can say that the sine curve is the same as the cosine curve shifted to the right by pi over 2, which I would write like that. So those two statements are true. The sine curve, the sine of an angle is equal to the cosine of x minus pi over 2. Therefore, if they give you a graph and they say, give me the sinusoid function of that graph, you have to make a decision whether you're going to use sine or cosine. And the decision is based on the fact that use whichever one has the least phase shift. Well, certainly the black curve, I'm always going to use it. That's got no phase shift at all. I would never call the black curve that. Even though it's correct, it's absolutely equal to the cosine of x minus pi over 2, but I'm always calling this sine of x because that has a smaller phase shift. Sine of x has no phase shift at all. Cosine of x minus pi over 2 has a phase shift in it. Now, if the phase shift is pi over 4, then either function works just as well. So the general rule is use sine or cosine or negative cosine, whichever one produces the smallest phase shift. Let's say this was my curve. Well, I'm going to call the green. I could talk about that as being a cosine curve that's been shifted, but I never would. That's the negative sine curve. Again, instead of using a phase shift on the cosine curve, I use the sine curve that's been reflected over the axis and has no phase shift. So the general rule here is always choose sine or cosine depending on which makes the smallest phase shift.
Okay.
So one last thing. Let me draw a function and let's graph it. This has got everything involved. I'm going to graph it one thing at a time. First thing I'm going to graph is that. That is y equals sine x. Okay? And I could quarter it up. That's pi over 2, that's 3 pi over 2. Now, the 2, let's take these one at a time. If I had y equals 2 sine x, in other words, what I've graphed is y equals sine x, and I'm going to take this curve and transform it by all of these transformations. I'm going to do it one at a time so you can see each one. That blue is y equal 2 sine x. Just have taken my sine x curve and vertically stretched it by a factor of 2. Now, in green, I'm going to graph y equals 2 sine of 4x. Well, 4 is outside the parentheses, so let's list a is equal to 2. What's b equal to?
4.
What's the period equal to?
1/2 pi over 2.
Okay. That means for the green curve, I got to draw the entire curve between 0 and pi over 2. So this curve, there's my quarter points, there, there, and there. So I've got to go up. In other words, this point is on the curve. This point is on that curve. This point is on that curve. And that point is on that curve. So in green, I'm going to draw that. I'm going to go up to there, down to there, down to its low, and back up to there. That green curve is y equal 2 sine of 4x. You with me? I do think it's important to show these one at a time. And let me finish, even though we're a minute over. Let me do all of these. Okay? The pi over 4, because my b was outside my parentheses, then c is pi over 4. And not only that, the phase shift is pi over 4. As long as your b is outside the parentheses, then c is the phase shift. Okay? So the way I'm going to draw this in red is I'm going to go to the pi over 4 mark, which is right there, and I'm going to redraw the green curve. Well, first of all, I didn't quite draw the green curve right. It goes down to -2, like that. Okay, with me now?
Mm-hmm.
Okay. Now I'm going to take the green curve and move it to the right by pi over 4 and do it in red. Okay. That means it's got to do something like this. Oops, sorry. It's got to go up to its peak, got to come down to its bottom, got to go down to its bottom, got to come up to its peak, and that is, remember the period of this is pi over 2, So this point right there has to be 3 pi over 4. The difference between pi over 4 and 3 pi over 4 is pi over 2. And that's what's important, is that we got the period right. It's got to be pi over 2 from the start to the new start of the next period. So my red line is now y equal 2 sine of 4 times x minus pi over 4. It's only one last thing to do, the vertical shift. You don't have another color, so I'm going to use black. I'm going to take the red line that I just drew, not going to change its shape, just going to move it up 3 units so that it starts at 3 and not 0. Okay, well, here's where the red line started. So I'm going to go straight up, and that's where my new black line's going to, and I'm going to try to draw the red line perfectly. Got to go up to 5, got to go down to 1, and come up at 3 pi over 2. So finally we have our final thing, which is that function. Now, when you're actually doing these, like on a test, there's a slightly better way to do it, and that's to start with the phase shift and B. In other words, start with C and B.
Mm-hmm.
And when we get to that point, I'll run through it with you, but we're out of time for tonight. And I do think it's important to go through each one of these one step at a time to show you what A does, to show you what B does, to show you what C does, and to show you what D does. But if you're doing all of them at once, I'm starting with the phase shift. In other words, I'm immediately going to pi over 4, and I'm beginning my graph right there. Or up. Next thing I'm going to do is go up 3 units and begin my graph there. And I'm going to make sure the period is pi over 2, so it's going to end there. And I'm going to make sure the amplitude takes me up 2 from my starting spot. So that's 5. And takes me down 2 from my starting spot. So that's 1. And I end up with that second black curve. And that's sinusoid function in a nutshell.
All right.
It's a lot of material to absorb. We really covered a lot tonight and the last session we had. Hopefully you got as much out of this one as you got out of that last session. Knowing the trig function of any angle that's a multiple of 30, 45, or 60 is a very, very key skill that you have to have in trig. And knowing how to draw any sinusoid function is a very, very key skill that you have to have in trig.
Mm-hmm.
All right.
All right. Well, you have a good rest of your day.
You too, and have a Merry Christmas, and I'll probably talk to you after the holidays.
Sounds good. I'll see you later.
Good luck on your test. Bye-bye.
Yeah, you too. I mean, not you too, but thanks.